Okay, let's dive in. So our sun, it's on this really epic journey, right? We know it goes around the galactic center. It takes about 250 million years.
Right. The galactic year.
Exactly.
Yeah.
But get this, it's also doing this kind of up and down motion
Yeah.
through the main flat part of the galaxy, like
Yeah.
well, like a cosmic yo-yo.
Oscillating.
Yeah. And this oscillation, this up and down trip, they reckon it takes, what, maybe 60 to 90 million years for one cycle? That's pretty wild.
It is wild. And what's really fascinating is that this bobbing, this oscillation, it's not random at all. It's all governed by gravity.
Right, the pull of all the stuff nearby.
Yeah, exactly. All the matter in our local part of the Milky Way. And that means everything. The stars you see, the gas clouds between them.
And the mysterious dark matter.
And the dark matter.
Which we can't see, of course.
Right. So, okay, that's the big question for this deep dive then. How much stuff is there? What's the total mass in our neighborhood that's like calling the shots for the sun's movement?
We've been looking into a paper that really digs into how astronomers try to actually weigh this local area, mostly by tracking how stars move.
Yeah, and understanding this local density, it's actually pretty fundamental. It tells us about our place in the galaxy, and the forces acting on us. It could even potentially influence things like, well, the conditions for life here in our solar system over cosmic time.
Wow, okay. So it connects back to us.
Yeah.
But measuring all that, especially the invisible dark matter part, that sounds like a huge challenge.
Oh, it absolutely is. I mean, dark matter, it doesn't give off light, right?
Right.
It doesn't interact with light. So we can't just, point a telescope and see it. We only know it's there because of its gravity.
So you see how other things are moving because of it.
Precisely. You infer its presence. Early on, people tried to estimate the mass just by, counting the stars they could see.
Which is like guessing the weight of an iceberg just from the bit sticking out on the water.
Exactly that. You get a lower limit, basically. You know there's probably more, but you don't know how much more.
Okay.
So this specific challenge in galactic dynamics, it's often called the KISS problem.
Key's problem.
Yeah, K-subs. It represents the gravitational acceleration, the pull towards the galactic plane, right here where we are.
Ah, okay.
And the way you measure KISS is by looking really carefully at the density and the velocities of certain types of stars. We call them tracer stars, stars whose properties we can measure well.
Gotcha. And I guess that's where space missions come in handy, like Hipparcos.
Exactly. Hipparcos was a huge step forward. Before Gaia, it was really the benchmark.
What did it do differently?
Well, it measured star positions and, crucially, their proper motions and parallaxes, which gives us distance much, much more accurately than we could from the ground.
Right, better data.
Much better data. And for more stars. It let astronomers use bigger samples like bright A-type stars or K-giant stars over larger distances. And, importantly, Hipparcos also helped refine estimates for the density of the visible stuff, stars, and gas near the sun.
Okay, so before Gaia came along with its, billions of stars, what was the picture looking like based on Hipparcos data? What did we think we knew?
So there was a really key study back in 1998 by Kreze and colleagues. They used those luminous A stars that Hipparcos measured well, and they calculated a local dynamical density that's the total mass needed to explain the star's motions. And they found it was, pretty much compatible with the amount of visible matter they could account for.
So no obvious need for extra dark matter right here in the disk.
Exactly. Their conclusion was basically, okay, we know the galaxy needs a lot of dark matter overall to explain its rotation.
Oh, right, the halo.
The big dark matter halo. But this study suggested the halo was probably roughly spherical, and not much of that dark matter was concentrated down here in the thin disk with the stars.
So the dark matter was thought to be this big diffuse cloud around the whole galaxy, not mixed in with the spiral arms.
That became the sort of prevailing view, yeah. Other studies using Hipparcos data, different stars, different methods, they mostly pointed towards the dark matter being mainly a halo component, not a significant disk component right near us.
Okay, so then fast forward. Gaia arrives. Billions of stars, incredible precision. How did that change the picture? It sounds like it must have been revolutionary.
Oh, completely. Gaia is just on a different scale. The precision of positions, distances, motions, It's staggering.
Uh,
And one of the early influential studies using Gaia's second data release, DR2, was by Widmark in 2019. He built a model of the local matter density.
what kind of model?
He assumed it was, reasonably smooth, symmetrical above and below the galactic plane, and decreased as you went further away from the plane. Pretty standard assumptions, really.
Okay. And what did his Gaia analysis find? Did it confirm the Hipparcos view? Or?
Well, this is where it gets interesting. He looked at multiple groups of stars, about 25,000 in each group. And consistently, his results showed a matter density that was significantly higher, very close to the galactic plane within about 200 parsecs, or 650 light years, than those earlier models suggested.
Higher, so more stuff nearby than expected.
Yeah. He called it a possible surplus of matter. He suggested maybe we'd underestimated the amount of cold gas hiding there in the disk.
Interesting. More ordinary matter, perhaps. What about the sun itself? Did Gaia refine our understanding of its position and motion?
Yes, Widmark's work also gave updated values for the sun being slightly above the geometric midplane
Okay.
and moving upwards, consistent with that ongoing oscillation we talked about.
Right, part of the yo-yo cycle. So Gaia was already sharpening the picture, finding maybe more mass close by. Did things evolve further with more Gaia data?
They did. Widmark was involved in another, more extensive study in 2021. This time they used even more stellar samples, looked at different regions around the sun, trying to account for, variations across the neighborhood, which always complicated things.
Right, making it more robust. And what did that bigger study show?
It showed a really clear trend, actually, across all the different regions they looked at. The total mass density seemed very strongly peaked right near the midplane, within that first 60 parsecs or so.
Okay, very concentrated.
Very concentrated. But then it dropped off quite rapidly with height above the plane.
Faster than expected.
Faster, yes. And they pointed out something intriguing. The low density they inferred further out, say above 300 parsecs, seemed kind of inconsistent with how spread out the stars themselves are in the disk. The stellar disk has a certain thickness or scale height, and the inferred mass distribution didn't quite match. This hinted that maybe the disk isn't in perfect, smooth equilibrium. Maybe there are time-varying things going on.
A galactic disk isn't static. It's rippling or something.
Kind of, and Gaia actually gave us direct evidence for this. A huge discovery. The Milky Way's phase-space spiral.
Phase-space spiral? What on earth is that?
Okay, so imagine you plot stars not just based on their position, but also their velocity, how fast they're moving, and in what direction. That's phase space.
Got it. Position and velocity together.
Right. When astronomers did this with Gaia data for millions of stars near us, these faint but definite spiral patterns emerged in the plot. It was first reported by Antoja and colleagues in 2018.
Wow.
And it tells us the disk isn't in a smooth, steady state. It's been disturbed somehow. It's not in perfect equilibrium.
A spiral pattern in how stars move? That's amazing. What could cause that? A disturbance?
That's the million-dollar question still being debated. One strong possibility is a past interaction, like a smaller satellite galaxy, maybe the Sagittarius dwarf galaxy, punching through the disk sometime in the past.
Like a gravitational ripple effect from a collision?
Sort of, yeah. Or it could be something internal, maybe instabilities related to the galaxy's central bar structure, buckling or warping.
Okay, so the galaxy might have gotten bumped, or it's vibrating internally. Does this mess up the measurements of local mass density?
Right.
If things aren't in equilibrium.
You'd think it would make it harder, right? But here's the clever part. Researchers are now actually using these non-equilibrium features, like the phase space spiral, as new tools.
Using the problem to find the answer.
Exactly. Because the shape and evolution of these spirals are sensitive to the underlying gravitational potential, the very thing we want to measure. One study used these time-varying patterns to estimate the local halo dark matter density, and even put an upper limit on whether there could be a hypothetical thin disk of dark matter, which earlier studies seem to rule out. The idea is these aren't just messy details, they contain information.
That's really fascinating.
Yeah.
Turning noise into signal.
Yeah.
Okay, so let's bring this back home. We have the sun doing its oscillation. We have stars moving in unexpected spirals. We have visible matter and this elusive dark matter.
Yeah.
What are the bigger implications? Why does this local cosmic environment matter to us here?
Well, like we hinted at, the sun's path through the galaxy, how high it goes above the plane, how often it crosses. This could matter for long-term habitability.
How so?
For instance, passing through denser regions of the disk might increase the chance of close encounters with other stars or dense gas clouds.
which could nudge comets from the Oort cloud inwards.
Potentially.
Okay.
Or change the cosmic ray environment, the radiation exposure for the solar system. These are long-term effects, obviously, but they connect our local dynamics to, well, our home.
Right. It's not just abstract numbers. And what about the dark matter specifically, knowing its density right here?
That's crucial for a whole different field. The direct detection experiments.
The lab's trying to catch a dark matter particle.
Exactly. Deep underground, shielded from other radiation, they're hoping a dark matter particle occasionally bumps into one of their detector atoms. But the rate at which they expect that to happen depends directly on how many dark matter particles are flying around right here near Earth.
Yeah.
It depends on the local dark matter density.
So you need to know how much stuff is actually there to know what your chances are of detecting it.
Precisely. A higher density means more potential interactions. A lower density means fewer. It's a critical input for designing and interpreting those experiments.
Okay, that makes total sense. So after all this work, Hipparcos, Gaia, analyzing spirals, where do we stand now? What's the current best guess for the local dark matter density?
Well, there's still a bit of a range, as you might expect. A review by DeSalis and Widmark in 2021 looked at many different analyses. The studies focusing just on the local neighborhood tend to find values around, say, 0.4 to 0.6 GeV per cubic centimeter.
GeV per cubic centimeter. How dense is that?
It's incredibly diffuse. To put it in more astronomical terms, that's about 0.011 to 0.016 times the mass of our sun in a volume defined by a cubic parsec. A parsec is about 3.26 light years, so a cubic parsec is a huge volume.
So really, really empty, but not quite zero.
Exactly. Now, analyses that look at the galaxy more globally tend to find slightly lower values, maybe more like 0.3 to 0.5 GeV per cubic centimeter.
Okay, so still some variation depending on the method, but we're zeroing in on a range.
We definitely are. The precision is way better than it used to be, thanks largely to Gaia. And this isn't the end of the story, of course.
Yeah.
No, Gaia is still releasing data. Future data releases will have even better measurements for even more stars, fainter stars, stars further away.
So the picture will get clearer still.
Absolutely. We can expect more refinements, a better understanding of these non-equilibrium features, and hopefully an even tighter constraint on that local dark matter density.
All right, so let's sort of wrap this up. We started with this cool image. The sun, our sun, oscillating up and down through the galactic plane maybe every 60 to 90 million years.
Driven by local gravity.
Right. And measuring that gravity, weighing the neighborhood is tough, especially with dark matter involved. We saw how Hipparcos gave us the first really good look.
Suggesting dark matter was mostly in the halo.
But then Gaia came along, a total game changer, finding maybe more mass close to the plane than we thought and revealing these amazing phase-based spirals.
Yeah, showing the disk isn't perfectly calm, it's dynamic.
And now we're using those dynamics, those spirals, to try and get even better measurements, especially for the local dark matter density, which is key for detection experiments.
That's a pretty good summary, yeah. We're getting a much more detailed and dynamic picture of our corner of the galaxy.
So here's something maybe for you to think about. This dynamic neighborhood we live in, with stars bobbing up and down, ripples from past events, this pervasive dark matter, how might all this continue to shape our solar system's future? You know, its evolution, maybe even its long-term habitability over the eons to come.
Yeah. It really makes you consider the interplay, doesn't it? Between the visible galaxy we see and the invisible forces constantly reshaping our cosmic home. A lot left to discover.